Now, Mr. Professor Manzoor Ikram is here. We will listen to him. He will teach us entanglement engineering subject. Okay.
I'm Dr. Manzoor Ikram from National Institute of Lasers and Electronics, Pakistan. I'm very much thankful to Professor Orkin here. He invited us to give our research over here. So I will have probably 4 talks today, tomorrow, and on Friday. The topics I plan to cover here are quantum entanglement. All my 3 talks today and tomorrow will be on quantum entanglement, how we can generate entanglement, how we can manipulate entanglement, how we can these entanglement when interact with the environment, they degrade and they degrade their usage in the quantum computation will get some losses. So in order to stop this degradation, we should have some schemes to increase the entanglement or to protect the entanglement. So I will talk about this entanglement kind of things. First topic today will be on entanglement generation. Here in the entanglement generation, I talk about the atom field, and atom-atom entanglement. And then about 2 modes of fields, how 2 modes of field can get entanglement. And then I will talk about continuous variable, and lastly about quantum dots and surface plasma. Because in photonic quantum computers, we can have quantum computers on chips. This quantum dots kind of stuff can give an idea to have quantum computer on chips. Then I will talk about the decoherence. Yesterday we have talked on decoherence of single qubit. How this single qubit behaves when it interacts with the environment. So I will give some more explanation how this decoherence affects on the entanglement. Entanglement dynamics in anticipatable environments. I will see that how entanglement degrades. And then entanglement stabilization, enhancement or protection, how we can protect the entanglement, how we can enhance the entanglement during operations. And environment engineering is another topic of how we can improve, how we can engineer the environment to increase the entanglement. If I find time, then I will discuss the teleportation of entanglement. Because in the quantum computation, no Bloom theorem does not allow to copy the state, quantum state from one place to another. To transfer the information or transfer the data from one register to another, the only way is teleportation. We should have some teleportation schemes to transfer the data from one register to another. So I will talk about this quantum teleportation. And finally, these 3 talks are theoretical talks. In the final, that is brief about quantum information research and NLO. It is all experimental. We have laboratories on quantum optics and quantum imaging, and this is all for quantum computation, quantum communication, quantum imaging. We have the laboratories at NLO. So in the last lecture, I will talk about our activities which are doing at NLO. So very basic for this qubit. For the last 2 days, you have been learning about this qubit. Qubit is a superposition state. It has 0 and 1. This is a qubit in matrix representation. These are the column matrix. 0 is 1, 0, and so this is very basic. There is no need to explain further. This qubit can be realized in many ways. Qubit can be realized in spin-up particle. If we have spin up 0, spin down 1. So this is the qubit. Qubit can be 2-level atoms, a ground state atom or upper state atoms. This is a qubit. We have to designate 0 and 1 to the states. If it is ground state, 0. If it is excited state, it is 1. Qubit can be in photon polarization state. Just before this lecture, we have a very nice talks on photonic quantum computers. So photons can be used in quantum computation. There are several properties of the quantum photons. The polarization is one of the property. Polarization, frequency, number of photons, photon energy. There are several variables associated with photons. They all can be entangled, can be in superposition states. But my focus area in these three talks will be a photon number states. Photons, number of photons in the cavity. We can have 0 photon or 1 photon, this qubit we may have inside the qubit. And because of this, it was the work of Harosh, who got the Nobel Prize in 2012. He had schemes to have a photon inside the cavity. So capturing a photon, because of this research work on capturing a photon in cavity, he got the Nobel Prize. So my talk, most of the talk will be focused on this, photons inside the cavity. There are some other ways. We may have quantum dots, we may have superconducting quantum circuits, we may have ion traps, nitrogen vacancy centers. So there are several candidates for the quantum computation. Why we use these qubits for quantum computation? You know that classical bit is 0 or 1. It is either 0 or it is 1. But in quantum mechanics, it is simultaneously 0 and 1. When we increase from 1 qubit to 2 qubits, so classically it is 2 qubit, but in quantum mechanics, we see that these 2 qubits can be encoded into 4 numbers: 0, 1, 2, 3. So 2 qubits can be encoded into 4 numbers. And these 4 numbers can be written as the states, in the form of the states. And these states can be in superposition of this. This is a superposition state of 2 qubits. It is 2 qubits, but it is a superposition of 4 states. So it is a kind of parallel processing. We are increasing the number of states, number of particles. It is only 2 particles, but the possibilities are 4 possibilities. If we have 3 particles, then we have 3 particles, so possibility of 8. 2 raised to power n, 2 raised to power 3 becomes 8 superposition states. So only 3 particles can have 0, 0, 0. So these 8 possibilities. In 4 particles, we have 16 possibilities. Or if we have 1000 particles, if we have 1000 particles, in case of 1000 particles, we may have 2 raised to power 1000, that is greater than 256. That is the number of particles in the universe more than the number of particles. So very less number of particles, very less number of qubits can have a huge number of parallel processing, huge number of very large number of superposition states. It is a kind of parallel processing. We have operation only 1 qubit. If we change only 1 qubit, it changes all the 16. If in case of 3 qubits, 3 particle system, we have 8 states, superposition of 8 states. If we apply a NOT gate will be swap. We have 0 or 1 only. If we swap 1 particle, let's say this is a 3 particle state 0, 0, 0, 0, 1, 0, 1, 0. This is 8 numbers encoded in these binary numbers. If we apply a gate, swap gate or NOT gate, what does it, what is the purpose of this NOT gate? Just swap this 0 to 1. Here 0 becomes 1. Here 0 becomes 1. 0 becomes 1. And this 1 becomes 0. We did not change any other qubit. We applied NOT gate to the first qubit only. So applying a NOT gate to the only 1 qubit, we change this all 8 numbers. This 0, 1, 2, 3, 4, 5, 6, 7, 8 is changed into 4, 5, 6, 7. This number is changed. So only one operation is applying on all the 4, all the 8 states simultaneously. So it is a kind of parallel processing. So there is a huge advantage of increasing the qubits, number of qubits. If we increase the qubits, we get the parallel processing, our computational speeds get speed up. So I will see that when the number of qubits increased, so there are two possibilities. The qubits can be separable or qubit cannot be separable. If the qubits are separable, if there are two qubits, 00 and 01, if these are separable, we call it as an entangled state, a separable state. However, if it is not this, we see these states, we cannot separate a qubit. So it is a non-separable state. It is an EPR state. We call it as entangled state. The states which cannot be separated, these are entangled states. Mathematically, it is a state of two or more quantum systems that cannot be expressed as the product of the states. These are entangled states. For entanglement, it is necessary condition that the two particles combine together, interact, and then get separated. So when they get interacted and separated, they have some connection, they have some correlation between them. There is some connection between them. This correlation is, in fact, this is quantum entanglement. Particle A, particle B, they have some interaction, correlation between them. If state of the A is alpha, state of the B is beta, they are not in product form, then they are entangled. If we write in a matrix form, so in matrix form, they cannot be written in product form. So definition, this is the definition of quantum mechanical phenomenon in which two quantum states of two or more objects have to be described with reference to each other. This correlation is not possible in classical. It is this kind of correlation is available only in the quantum mechanics and Einstein. Therefore, Einstein called it as a spooky action, because we take a measurement on one particle, you get the instantaneous information about the state of the other particle. This entangled states, there is several kind of entangled states. If you see this state is separable. If it is separable, it is unentangled. If you look, I'm talking about two qubit state. If this two qubit state, here you see that this zero is common in these two. So when zero is common in these two, this state can be written as this. Here you can take one common from right side, so this state can be written this. So these kind of states where we can have some common states, these are called partially entangled state. Or there are some states which cannot be written in the common form or in the product form, they are maximally entangled state. So entanglement, if we measure the entanglement, if we quantify the entanglement, so there is some limit from 0 to 1. Zero entanglement, it is separable states in between. This is one maximally entangled state, it is in between, this is partially entangled state. So there should be some phenomena, some mechanism to measure the entanglement. So for quantitative measurement of entanglement, there are three major schemes which quantify the entanglement, how much entanglement is there. Because the amount of entanglement gives you probability of success in the quantum computation. More entanglement, more successful, less entanglement, less success. So there are, so we should have some measurement of entanglement. There are three techniques, three ways. One is von Neumann entropy. Entropy is one way of measuring entanglement. What we do in entropy, we take partial trace, two qubit system. It is written in matrix form, rho AB. We take a trace on one of the particle. Let's say we take a trace on particle B. We take partial trace. This is the density matrix, where 1 is encoded as 0, 0, 2 is 0, 1. And when we take a partial trace, we get this matrix. We take partial trace over B. So this is a matrix. And we find the eigenvalues of this matrix. And we know that Schmidt decomposition says if number of non-zero eigenvalues are more than 1, then state is entangled. It is just it shows Schmidt decomposition shows that whether the states are entangled or states are not entangled. But if we take a sum, logarithmic sum of these eigenvalues of this partial trace matrix, we get a quantitative measure of entanglement, which ranges from 0 to 1. So this entropy gives you an amount of entanglement. Another is concurrence, Wooter's concurrence. Wooter concurrence is another way of finding quantum entanglement, quantified entanglement. But Wooter concurrence says that we may write the density matrix. State psi AB is entangled state. We write a density matrix of this entangled state through IJKL. This is the density matrix. Then from this density matrix, we apply this Pauli operators, sigma y, because it is a 2-qubit state. We apply this 4x4 matrix. This is a complex conjugate of this. We apply this one. So this M is a matrix. We find the eigenvalues of this matrix. The eigenvalues of this matrix is written in descending order. This lambda 1, there are 4 eigenvalues. It is a 4x4 matrix. 4 eigenvalues, lambda 1, lambda 2, lambda 3, lambda 4. If you write the maximum eigenvalue here and then subtract the other ones, we get a number. This number varies from 0 to 1. So it gives you a quantitative measure of entanglement. If it is 0, an entangled state. If it is 1, it is maximally entangled state, and in between, it is partially entangled state. So this Wooter's concurrence measurement on the entangled states gives you the amount of entanglement. Another is negativity. In negativity, we take a partial transpose. Again, we write a density matrix of 4 qubits. 4-qubit state, we take a density matrix, we take a partial transpose. Partial transpose on 1 qubit. It is just like taking a mirror. If you see yourself in mirror and then your left hand become in the mirror, it looks right. So we take a convolution kind of things. So this is partial transpose. And this partial transpose, after taking partial transpose, we take the eigenvalues of this matrix. And the negative eigenvalues, sum of all negative eigenvalues gives you if you have any one of the negative eigenvalues of this matrix, it shows that state is entangled. If we take a sum of all negative eigenvalues, it quantifies the entanglement. Entanglement is sum of all negative values. So these 3 techniques give you the amount of entanglement. It quantifies the entanglement. And these are all similar. If you take any entangled state, for example, if you take Bell states and you apply, this will be homework for you. Take a Bell state or any other entangled state, apply these all 3 criteria, you will get the amount of entanglement. And this amount of entanglement will be the same in all 3 cases. Now, I switch after giving some basics on the entanglement, I switch towards the laser matter interaction, how we can generate entanglement. This is a very basic kind of stuff. Savi and we have talks on this generation, on this laser matter interaction. When a laser interacts with atoms, what happens? When laser interacts with atoms, we have this Rabi oscillation. This electron goes up and goes down, goes up and goes down. We have this Rabi oscillations. These Rabi oscillations will give you an idea how much time you should have to entanglement. Let me see, when this laser interacts with the atoms, this is the Hamiltonian, which governs this interaction. Omega, this capital omega is the strength of the field. It is, we call it as Rabi frequency. It depends upon the strength of the field. This A and B, these are A is upper atomic, upper state, B is the ground state. This Hamiltonian is resonant. When the frequency of this laser is resonant with this atom, it means frequency of these two levels, and the laser, if it is same, it is resonant, then this is the Hamiltonian. And the state vector, in the first lecture, we said that psi1, psi is C1, C2. Ca is the probability amplitude of having atom in A, Cb is the probability amplitude of having atom in B. These amplitudes are not time dependent. Why it is time dependent? Because atom oscillates. There is some time here. At some time, atom will be found here, at some time, atom will be found here, and there is some time where atom will be found in the states. Atom may be in the superposition state. So we can see what are the times, at what times atom at A, or what time atom in B, and what are superposition states. How we solve this? We solve this state using Schrödinger equation. This is Schrödinger equation, H and psi. From this Schrödinger equations, we find this probability amplitudes, Ca and Cb. And Ca and Cb, these are sine of omega t by 2 and cos of omega t by 2 from Schrödinger equation. It is simple mathematics. We get a double differential equation, and we solve this differential equation. From this differential equation, we get this probability amplitudes. And from this probability amplitudes, we get the probability. This is the probability of finding the atom in excited state, and Pb is the probability of atom finding in ground state. So we get these two probabilities. When we plot these two probabilities, so this is the probability distribution. We take Pa, this is the psi over psi. This is probability of finding an atom A, right? We plot this probability of finding A. This is sine square function, so this is the plot. This is the complete plot up to pi. If we plot this one time against PA, we get this sine square function. If we truncate the interaction of atom with the cavity, interaction of laser with the atom, if we truncate at this place, right? This place means it is pi by 2, right? This is pi by 2. Pi by 2 means if you take omega t over 2 is equal to pi by 2, this is pi by 2, we call it as pi pulse. If you take pi pulse, means probability of atom finding atom at excited state was 0, it becomes 1. It is atoms which started from the ground state, it ends up in the excited state with this pi pulse. So pi pulse is changing the atomic state from ground state to atomic to excited state. However, if we truncate our interaction, this interaction is controllable. We can control this interaction of atoms using controlling the time. If we truncate our interaction over here, this is in between A, and it is in between B. So if we truncate our interaction over here, then our B state, the ground state, will convert into the superposition state. It turns into the qubit state. Qubit. So this we call it as pi by 2 pulse. Pi pulse is changing one state to another. Pi pulse is changing 0 to 1, and pi by 2 pulse is changing 0 to 0 plus 1. If A is 1, B is 0, and it is preparing, this pi by 2 pulse is preparing a superposition state. So we got these two pulses, and we can control these interaction time. And this is a little about quantum electrodynamics. I was talking about the interaction of laser with the atoms. Now I take, instead of laser, I take cavity field. Laser is a classical field. in the earlier 2 days, we have a lot of discussion that this laser is a coherent state, and coherent state displays vacuum state, it is a classical state. Now I come towards the quantum states, Fock states. The state inside the cavity is Fock state. It is a quantized state. And the quantized states interact with the atom. Here is a two-level atom. It has some decay rate. Decay rate means this atom interacts with the environment. This atom is trapped inside the cavity. Cavity has some quantized states, number of photons inside the cavity. And the cavity also has some decay rate, kappa. So the Hamiltonian, which describes this interaction of cavity field with the atoms. This one, this is the free part of the atom. This Hamiltonian is the free part of the field inside the cavity, and this is interaction Hamiltonian. Again, this interaction is resonant interaction. The field of the cavity is resonant with the atomic frequency. So this is the Hamiltonian which interact. These are atomic raising and lowering operator, annihilation and creation operators. And Sabi last time described this annihilation operator and interact with this, and we get decrease in N, creation operator increases number of photons, and this is number of operators. So you have all these. No, what happens? I was talking about the Rabi pulses, and this is experimentally verified. It is not only the theory, but it is experimentally verified by Harosh, because this Harosh what he did, he interacted with the atom with the cavity field. Cavity has a vacuum inside. If cavity has vacuum, and the atom interact with the cavity field, and he got this Rabi oscillation. This Rabi oscillation is experimentally determined by Harosh. Again, if we truncate over here pi/2 pulse, you know that dimension of the cavity is fixed. The velocity of the atoms we can vary, or it may be fixed. What can control the interaction time? Interaction time can be controlled by applying a voltage, applying a field over this cavity. If we apply a field over this cavity, then this cavity becomes resonant for a specific interval of time. So we can control the time by some switch, by applying voltage. So making this cavity resonant and off resonant, we can control the interaction time. So if we truncate, if we allow the resonant interaction for only this time, pi/2 pulse, we find this, we pass this atom in excited state. If the atom passes in the excited state, then it will not contribute any photon inside the cavity. However, if atom passes from this cavity and found in ground state, then these atoms contribute a photon inside the cavity. And this interaction, we call it as pi/2 interaction. And this pi/2 interaction, we will see it is pi/2. It is a general kind of things. Generally, if atom do not contribute in the cavity and exit in excited state, so atom exit in excited state, no photon, and this is the probability amplitudes. If the atom contribute a photon inside the cavity and exit in the ground state, so this is the probability. And this probability, analytically, you can find from Schrödinger equation, you can solve, and it is experimentally verified by this one. So this is the equation which governs this interaction of two-level atom, the cavity field. However, if there are n number of photons inside, this is the state which ends this equation. If we have n number of photons inside the cavities, so this is the equation which governs passage of two-level atoms from these two cavities. Here we see that when two-level atoms interact with the cavity, this is the state which comes atom initially in excited state and vacuum inside the cavity. This state ends up here. Here we see that if we have pi by 2 pulse means we truncate our interaction over here. Pi by 2 pulse means this omega t by 2 is equal to pi by 4. This state is generated. It is a atom field entangled state because it is entangled state between atom and field. However, if we have pi pulse means we truncate our interaction over here. If excited state, this is the initial state, right column, left column is initial state, right column is later state. If atom is in excited state and found in ground state, it means it has contributed a photon inside the cavity. We can generate one photon state in the cavity. If atom is initially in ground state and there is a one photon in the cavity, then this one photon will be absorbed by this and atom will exit in the excited state. If ground state atom, no photon, it remains because there is no way to get absorbed. However, if atom is in superposition state, we can prepare the atom in superposition state. We see that truncation of laser pulses. If we truncate our laser interaction with the cavity, with the atoms, we can prepare this superposition state. If atom is initially in superposition state and there is no photon inside the cavity, then this state is converted into this state is swapped to the cavity field state. So we can interchange the atomic state to the cavity state, photonic state. And photon state can be converted to an atomic state. This is a kind of swapping. No, I come to that. This is the basic mass which governs how we can add photon inside the cavity. Now I talk about how we can generate cavity field entangled state. For cavity field entangled state, we should have two cavities. Here we have two cavities, cavity A and cavity B. We pass a two-level atom initially in excited state. When it passes from first cavity, then we apply a pi by 2 pulse. This atom is passing from there here, pi by 2 pulse. What happens with the pi by 2 pulse? We get a superposition of atomic state with a cavity field. And cavity B, because atom only passes from the cavity A. Atom when passes from cavity A, here at this stage, we have this state. This is atom field entangled state. And from the cavity B, we have pi pulse. So we have the interaction time. Interaction time is pi by 2 pulse in first cavity and pi pulse in the second cavity. If we have pi pulse in the second cavity, this entangled state inside the cavity is generated. 0 photon in first cavity, 1 in the second, or 1 in the first, 0 in the second. So this state can be generated inside the two cavities. Now, using this mathematics, this phenomena, because this entangled state is generated experimentally by Harold-Shroup. Harold-Shroup use this interaction and this controlled interaction to generate entangled field state in two cavities. I talk about how we can generate other entangled states. There are several applications. If we increase the number of qubits, we see that computation speed up. We get speed up in the computation. So we thought about increasing the qubits, increasing the number of photons inside the cavities. So one way is having fixed number of photons. An entangled state in two cavities having fixed number of photons. Fixed number of photons means earlier Harold-Shroup showed that one photon in each cavity, either in cavity 1 or cavity 3. We said that if we pass two atoms, instead of passing one atom, if we pass two atoms and we calculate the interaction time, if we control the interaction time, then we can have this kind of entangled state. This entangled state, we call it as entangled state of fixed number of photons. Because we see that there are two photons Zero photon in one cavity A, two there, or it is one photon in both cavities, or two photons in one cavity and no photon. So total number of photons inside the cavities is two. This is entangled state for fixed number of photons. How we do this? Because for two cavities, for comparing EPR states, we know the time. We know the interaction time. It is pi/2 pulse and pi pulse. Pi/2 pulse in the first cavity, pi pulse in the second cavity. What should be the time? What should be the interaction time to generate this entangled state? We pass this first atom. Sequentially, we pass first atom and then second atom. So yesterday we listened about unitary operator. Unitary operators is a way of quantum optics calculations. We apply a unitary operator to the initial state, we get the state after some time t. So unitary operator, this is the way of finding unitary operator. Exponential iota Hamiltonian time t into h. This is the way of finding Hamiltonian unitary operator. So unitary operator for interaction of atom with the cavity, interaction of single atom with the cavity. This is the unitary operator. Cavity field is quantized. So this is a unitary operator. We apply this unitary operator to the initial state. Initially, what is the initial conditions? Initially, both the atoms are in vacuum states and atom is in excited state. We apply these two unitary operators to this initial state. What we get after some time t, when after passage of first atom, when the first atom passes through these two cavities, we get this state. Atom will pass in excited state, no photon. Atom will be in ground state, contributing a photon in cavity B or contributing a photon in cavity A. And these are the probability amplitudes. And from these probability amplitudes, this is the passage of only first atom. Now this state becomes the initial state for the passage of second atom. Earlier, this was the state, this is the excited state, I denoted this is excited E. These are the ground state, so designate this ground state probability issues. So this becomes, okay, another condition. We pass the atoms from the two cavities, and then the condition we find the atom in the ground state. So if you find the atom in ground state, so we make a measurement. Making a measurement on the quantum state, it collapses, it gets collapsed. So this state, we make a measurement on the atom. It's the condition that atom, we detect the atom in the ground state. When we detect the atom in ground state, so this state becomes 0, we get only these two states. And we have to renormalize it. So after renormalization, this state becomes the initial state after passing two atoms after passing one atom from the two cavities. So we apply this is the initial state for second atom. We apply again unitary operator sequentially on the second on this initial state, and we get this state. And again we find this atom in the ground state. So this is the final state. It has 0, 2, 1, 1, and 2, 0. And atom is in ground state. So this state we get. Now the next thing is to calculate the time. How we can calculate the time? In order to calculate the time, we apply some conditions. These all probability amplitude should be same. To keep this probability amplitude same, we calculate the interaction time. This table shows that we plot this earlier. This is the Hiroshima. We prepared this entangled state. For this entangled state, for the one photon, it is 100% probability that by keeping this interaction time pi/2 pulse and pi pulse, it is 100% probability that this entangled state will be prepared. However, if we take these interaction time was calculated from here. These should be equal. From these, we calculated these interaction times. So there is 95%, 95.35% probability that this entangled state of having two photons in the two cavities will be generated. It has a lot of applications. This kind of entangled state have application in quantum teleportation, in quantum computation. Next, we can generalize it. We can apply the same criteria. Passes number of atoms in the two cavities, 1 atom, 2 atoms, 3 atoms, n number of atoms. For n number of atoms, we can generate n photons, n photonic states in the cavities. Applying simple mathematics, same mathematics, unity operator, we apply sequentially, unity operators, utah A and utah B, and applying the condition that atoms are detected in the ground state, we end up with this state, right? Where these are the probability amplitudes having sine cos function, and from the sine cos function, when we solve it, we can find the interaction times. And so this entangled state can be generated. It has n number of photons inside the two cavities. What about three cavities? Can we have, because we know that increasing the qubits increases the computational speed up. Can we generate three photons entangled state in the three cavities? Yes, we can generate. We pass atom in the three cavities and interact atoms in the ground state. This entangled state, W state, is generated. Again, same procedure, we apply unity operators one by one, and we get interaction time. These are the interaction times. If we control this interaction time, we can generate this W state. Can we generate this GAZ state? For W state, we have this cavity in line. We pass say atom in this atom sequentially from one cavity, second cavity, and third cavity. For GAZ state, we arrange the atom, we arrange the cavities in this way. First atom passes from this cavity and this cavity, second atom passes from first cavity and this third cavity. So initially we prepare the superposition state in the cavity, and these two cavities are taken as vacuum states. So this is the initial state. We have atoms in the ground state, first cavity, cavity A in the superposition state, cavity B and cavity C in the vacuum state. We pass, after passage of two atoms from this cavity and applying same formula, same techniques to calculate the interaction time, we get these interaction time. If we control the interaction time, we can prepare this GAZ state. And you know, the controlling the interaction time is not a difficult task, because we apply voltage over here, ground here, etc. Here we apply voltage. So we apply electric field on the cavity. It makes cavity resonate with the atoms and offers. So we apply these interaction times. So we make the cavity resonate for this interval of time. We can generate this state. And similarly, we can generate n number of photons, n number of cavities. We apply the same procedure. We can generate cavities, n number of cavities, right? And we can generate GAZ states in the n cavities, because we should have one cavity where all the atoms passes, all other cavities may be taken on array or on the array table. We passes the atoms from the cavity 1 and the cavity 2, and this cavity 2 is passed away, and second atom with this and this. So with these schemes, passage of atoms one by one to the two cavities, we end up this GHG state. And similarly, we can generate. This scheme shows that how atoms can be made resonant with the atoms. This cavity field can be make resonant with these atoms. We apply a field, we control this voltage from computer or some other devices. So this interaction time can be experimentally controlled. By this, I have earlier shown that this cavity field can be converted into atomic field. Atomic field can be converted into cavity field by using pi by 2 pulses and pi pulses. So this is in this way we can generate. This is the original work of Harosh. Passes atom 1 and give pi by 2 pulse. Atom 1 pi by 2 pulse. This state is generated. Atom 2 for pi pulse. This state is generated. This is an entangled state among two atoms. Another ways can we have in photons there is one property of photon is the number state, Fock state. We can generate entangled state among the Fock state inside the cavities. Another variable is frequency. We may have multiple modes inside the cavity. We can generate entanglement on multiple frequency or multiple modes. We may have, if we passes instead of 2-level atoms, we pass 3-level atoms. This is a 3-level atom. A, B, and C. A, B are two excited states. C is the common ground state. If we pass 3-level atoms in the cavity, this cavity is bimodal cavity. It can support 2 modes, and these are we have resonant interaction of these atoms with the field. Again, this is initial state. We prepare the atom in the superposition of A and B, and the two cavities are in two cavities. This is one cavity having 2 modes. These 2 modes are resonant with atoms, atomic positions. This AC and BC, and the 2 modes are in vacuum. This is the Hamiltonian, which governs this interaction. After when we solve this equations using Schrodinger equation, we get this. When the atoms, this is the initial state of the atom. Atom in superposition, both modes are in vacuum. So if atom is in excited state, it remains in excited state. It means there is no contribution of photons. If the atoms if atoms in the B state, no contribution, it is 0, 0. If it contribute the photons in the cavity, it may be either from A. If it is from A, the photon is in A mode. If it is photon comes from this B, it is a B mode. So this is the state, and from this controlling the time of these probability amplitudes, we can generate entangled state. If we have these times T1 and T2, so this entangled state is prepared. If we have these interaction time, then this field is this 2-mode field is generated in the cavity. Similarly, if we have n modes inside the cavity, we have such cavity which can support n number of modes. We can have this GSC state inside the cavity. And these 2-mode cavities, we may have quantum beat lasers. Quantum beat lasers, similar scheme. We have 3-level atoms, which supports 2 modes, and when it passes these 2-level atoms in the two cavities, these are the atoms, and these atoms are trapped in the 2 modes cavity. Then we may have entanglement. And this shows the entanglement among 2 modes of the covalent emission laser, quantum beat lasers. How much time I have? Should I stop here or continue for the beam sessions?
We have 12 minutes. We have 12 more minutes.
Okay, I will briefly talk about entanglement using beam splitter on discrete variables. There are two ways. Yesterday, we talked a lot about beam splitter. Beam splitter can generate entanglement, but instead of talking entanglement, he was using G2 functions. G2 functions mean non-classicality. He shows that when one photon, one input, and two and vacuum on the other, and when we calculate the second order correlation function, it shows that the state generated from these beam splitter is non-classical state, is a quantum state. Here I will show that in terms of entanglement. Beam splitter has two inputs, A1 and A2. These are the two inputs to the beam splitter. A3 and A4, these are the two outputs of the beam splitter. If we take classically, we talk about classical interpretation. Classically, these are the two input modes, two output modes. These are the transmission or reflection of three. This three can be written as A1 is transmitted and A2 is reflected. So in this metric from this one. So for lossless beam splitter, this is the transformation. If it is a 50-50 beam splitter, then classically these modes A3 and A4 are related with A1 and A2. But there is slight difference in case of quantum states. We know that we have a lot of discussion on state is quantized or state is classical. Vacuum state is classical, coherent state is classical, while squeeze states are quantized states, focus states are quantized states. And when we talk about the phase space, X1 and X2, we have some uncertainties. These are equal 1/4. We call it as it is the classical state. When uncertainties are squeezed, we call it as quantized states. In case of fog state, mostly I'm talking about the fog state. In fog state, we have the amplitude, that is number of photons fixed, and we have uncertainty in phase is infinite. So we cannot talk about in phase, and we talk about the fog state on the number of photons. So here we see that what is quantum state and what is classical state. In quantum states, the behavior of the beam splitter is a bit different. A3 and A4, Sabi and were last day talk about this. This A3 and A4, the output modes, these are related with this input A1 and A2. So this is the transformation. This A1 and A2 are transformed to A3 and A4. This A3 and A4 are written in this unity operators. And this unity operator is this one. This is the unity operator. It acts on this A1 and A2. So this is a quantum mechanical treatment of beam splitter. Beam splitter is the simplest device everybody has in the labs. So we have seen yesterday that if vacuum on both the modes, we get vacuum on these two modes. So simple, if we apply this transformation, vacuum first mode and second modes, if these two modes are in vacuum, we get vacuum output. However, if we have vacuum on the first mode, here we have vacuum, and in two, we have one photons. It is a focus state. It is maximally, it is a quantized state. It has uncertainty in phase. So it is a quantum state, this one photon here, vacuum here. This is the initial state. With this initial state, we can write this state as this one is on two. So this two, instead of writing one here, we can write annihilation operator, creation operator of mode 2. So this state can be written as this one. So 0, 1 input state, we can write this one instead of we write 0 over here and we write a creation operator over here. And from this creation operator, we can from the transformation portion that this creation operators can be written in terms of output modes A3 and A4. We replace this A2 with this one, right? This A2 we substitute over here, and these are the modes 3 and 4. This creation operator applies on A3, third mode, and creation operator 4 is applied on this mode. So when we apply these creation operators on this vacuum states, we get this state. This is a EPR state, maximally entangled state. Simply, if we have vacuum on one mode, one photon on the other mode, we get maximally entangled state, this state. And when we make measurement, we will either get photon in the third, on the 3, or we will get photons on the 4. If we have vacuum in coherent state, you know, it is a displaced vacuum state. If you apply on first mode, it is vacuum, and the second mode, it is coherent state. Coherent state is displaced vacuum state. We write this coherent state instead of it is displaced vacuum state, and this is the displacement operator. So again, we can write this state into 3 and 4 using this displacement operator. When we apply this displacement operator on this fourth, we get on this 3 and 4, we get this diagonal state. This state is prepared. 3 we will have coherent state, and on 4 we will have coherent state. So when we have coherent state on one arm and we have vacuum on the second arm, we see that output is not entangled, it is product form. You may do exercise at your home. If you have one photon on one arm, one photon each on one arm, one photon here, one photon here. So because of this one, we may write this one as A1 dagger and A2 dagger. This A1 dagger and A2 dagger are converted from the transformation into A3 and A4. We showed that the transformation of A1, A2 into A2, A3, A4. We can write this A1 dagger, A2 dagger in this way. And when we apply this A3 dagger, A4 dagger on this A3 and A4, A3 is applied only on A3, A4 is applied on A4. When you apply this A3 and A4, we get 2 photons on 3 and 0 photons in 4. 0 photons in 3 and 2 photons in 4. So it is very interesting result. Yesterday we talked about this, that when we have 2 photons, 1 photon in each arm, we never get 1 photon in the output state. Either we get 2 photons over here, or we get 2 photons over here. So 2 photons are found in one arm only. So we generate this kind of entangled state. This mathematics shows, and experimentally you can verify it. If you have single photon sources, we can see that only one detector will click twice. It is not possible that both detectors will click. You inject 2 photons, one detector will click twice only. So it is interesting. So this entangled state is generated if we have 2 photons. This will be for your homework. If you have n photons in one arm and vacuum, you generate this entangled state. Same mathematics. If you have n photons in both the state, so you write this state in this form, and you may end up. It is a mathematics. You may end up this entangled state. If you have coherent state in both the arms, you will get separable state, because coherent state is not entangled. if you apply squeeze state in one arm, and if you apply squeeze state and vacuum on the other arm, you may apply squeeze thermal state. Thermal state, you know, this state inside this is a thermal state. If this thermal state is squeezed, you may get entanglement over here. So this is the summary. It shows that 0, 0, 1, we apply 0 and 1, we get entangled state. If you apply 0 and alpha, you get separable state. If apply 1, 1, it is 2 photon state. If apply coherent state, these are the separable state. So what you conclude from here, we conclude that for beam splitter, there are two inputs and there are two outputs. These two outputs, we measure entanglement. Whether these two outputs are entangled or not, it depends upon the non-classicality of the input states. If one of the input state is non-classical, then we get entanglement. If both the states are classical, then we don't get entanglement in the output state. So non-classicality on the one input is the necessary condition to have entanglement using beam splitter. I think at this point I end this. Thank you.